Okay, here I will discuss what I refer to as additional note number 1. Where I shall discuss the intuitive argument for Dirac's proposal, which led Feynman to develop a proposed path integral for quantum mechanics. There are 2 steps in this discussion. Step 1 is we first argue that action generates canonical transformation that takes the system from one term to another. So that's the statement. Action generates canonical transformation that take the system from one time to another. And then the second step is how to implement it quantum mechanically. So implementation of this result in classical mechanics, implementation in quantum mechanics. Okay, so let us first start with step 1. Recall canonical transformation. Canonical transformation is a transformation from an initial set of phase space variables, say xp, to another set of phase space variable x prime p prime, as a result of which Hamiltonian h goes to h prime, such that Hamilton's equation of motion are form invariant, such that Hamilton's equation of motion are form invariant. That means that x dot, which is given by del p of h, del p del h del p, and p dot. Okay, so let me write it this way: x dot, which is given by x h Poisson bracket, is del h del p, and p dot, which is ph Poisson bracket, is minus del h del x. This system of equation must go to a set where x is replaced by x prime and h by h prime. Now, this set of equations, this result follows actually from the fundamental Poisson brackets. This result is characteristic of the fundamental Poisson brackets. So this is the same as this statement, is therefore equivalent to saying that fundamental Poisson brackets are invariant under this transformation, which means that x comma x Poisson bracket equals p comma p Poisson bracket equal to 0 and x comma p equals 1, this must go to a new to the new set of Poisson brackets which are same. Now, Hamilton's equation of motion, this equation of motion, so these are the equations of motion. These equations of motion are obtained from what is called Hamilton's principle. Which says that the variation of the quantity integral dt ti to tf p x dot minus h x pt is equal to 0. And because we are demanding this same structure for the prime variable, we must have this 0 equal to integral dt ti to tf p prime x dot prime minus h prime x prime p prime t. Now, okay, now this with the condition, with boundary condition that delta x equals delta p equals delta x prime equals delta p prime equals 0 at t equals ti and tf. Because of these boundary conditions, we could relate the integrand here and the integrand here, because the difference between these two integrands must be a total time derivative. If that is total time derivative of a function of any pair of two variables, say xp, xx prime, xp prime, pp prime, then if it's a total derivative of a function of those two variables, then the result of this integral will be a boundary term, the function evaluated at tf minus ti, and the variations will be 0 because the variation of the function at the boundary must be 0 if it's a function of these variables, right? So therefore, we get an equation sorry, let me draw a line here. Therefore, we conclude that p x dot minus h x p t is equal to p prime x dot prime minus h prime x prime p prime t plus dg dt, where g is a function of any of the following pairs. x comma x prime, x comma p prime, x p comma x prime and p comma p prime. Now we are going to specialize to the first set, the first pair. So specialize to G being a function of x comma x prime. Okay, we just consider the first one, and then the same equation, then the chain rule will tell us that dg dt is del g del t plus del g del x times x dot plus del g del x prime times x dot prime. And if you substitute these expression in here, then you see that the term with an x dot factor can pair up with this term, and the term with x dot prime will pair up with this term, and this term will pair up with this and this together. Okay, so therefore, substituting this, we get p minus del g del x times x dot minus p prime plus del g del x prime times x dot prime minus h, which is function of xpt, plus h prime minus del g del t equals 0. Then you use independence of the variables to conclude that p must be del g del x, p prime must be minus del g del x prime, and h prime should be equal to h plus del g del t. This is the standard treatment of canonical transformation, and we get this key equation, key set of equations. Okay. Now, after this, we specialize to a specific type of canonical transformation, which says that x prime and p prime, the new set of phase space variables, are constants of motion. Okay. So what we are doing now is consider spatial canonical transformation generated by, say, s of x comma x prime comma t, such that x dot prime, which is the Poisson bracket x prime h prime, is equal to 0, and p dot prime, which is a Poisson bracket of p prime h prime, is equal to 0. You can argue that this kind of pair of variables should exist so because both the Poisson brackets of x prime and p prime with h prime must vanish, h prime must be independent of both x prime and p prime. So h prime must be independent of both x prime and p prime, and therefore is a constant. So what it says is that if you start out with any pair of phase space variables, say x and p, in which Hamiltonian looks non-trivial function of x and p, then we know that the dynamics is such that the value of the Hamiltonian for each trajectory is constant. So what it means that you are going to a different set of variables, coordinate and momenta, where that constant value itself becomes the Hamiltonian. Okay, so we, for simplicity, let's take that constant to be 0. Okay, so for simplicity, let's take h prime to be equal to 0. Okay, now what are the consequences of this consideration? So this implies, number one, if you go to this equation, oh, this is h, sorry, this should be h prime equals h plus del g del t. So this equation would imply that h prime equal to 0, so h is minus del s del t. So that's h, where h is a function of x and p is given by del s del x. So p is equal to del s del x and t should be equal to minus del s del t. This is number one. Then number two, p prime, which is given by this equation, which is minus del s del x prime. So minus del x prime of s, s being a function of x, x prime and t, and this must be a constant. Here x prime is also a constant. Constant means the equation of motion says that it is independent of time, doesn't evolve. Now this second equation writes p prime in terms of x, x prime and t, and therefore it can be inverted to write x in terms of x prime, p prime and t. So invert this equation to write x as a function of x prime, p prime and t. So now let us focus on this equation. What does it mean? So this is a function x written in terms of x prime, p prime and t, where x prime and p prime are constants of motion. Okay, now that pretty much is the structure of the solution of the dynamical problem, because then x prime, p prime must be related to the initial conditions. This pair x prime, p prime must be related to initial conditions. Initial conditions, and when you write x as a function of x prime, p prime, t, where x prime, p prime, t are related to the initial conditions x0 and t0, then that must be the solution. Must be the solution of the dynamical problem. Okay, so that means this x can now be interpreted as a trajectory. This coordinate transformation itself, it can be interpreted, is basically giving you the trajectory. The coordinate transformation between x with the primed variables itself give you the trajectory. Yeah, and number 3 is the equation that which equation should we use? Let's see. So number 3 is this equation where ds dt h prime is 0. Okay, so we can use this equation. On the right hand side you have ds dt, h prime is 0 and x dot prime is also 0 because x prime we have by construction x prime is a constant of motion. So this entire first two terms 0. So ds dt is equal to px dot minus h. So let us use that.